Okay, fantastic. Thanks so much. Thanks to Jacques and the organizing committee for putting together a lovely meeting. And it was really nice. I never had the fortune of meeting Bill, but it was really nice to hear some of the more senior members of the community. Apologies to the. It was really nice. It was really nice to hear stories about Bill from the more senior members of the community. So my talk is actually I did a title switch actually, a quantum dynamics model for LENR. This has been sort of the product of many years of work by Peter Hagelstein at MIT. Peter wished he could have made it to this meeting, but this week classes started at MIT, and he wanted to be there for his students. So this is our team, and our ambition is to modify nuclear reaction rates using tabletop configurations. And our sort of vision for the future is that in the 20th century, science learned to master electronic states and can precisely control electronic states. And in the 21st century, we'd like to do that for nuclei, to precisely control nuclear states. And we're inspired by Julian Schwenger, who said, one must ask if any conceivable mechanism now exists or might be devised whereby nuclear energy could be extracted by manipulations at the atomic level in 1990. So some will be familiar and will have seen various versions of this preprint, known mechanisms that increase nuclear fusion rates in the solid state. But this work has now been really sort of solidified and consolidated and has culminated in this paper, which is soon to be published in the New Journal of Physics. And in it, sort of the supplementary information has turned into a sort of a treatise, 200-some page document, which provides a very detailed quantum dynamics model, which we believe, Peter has had many models over the years, which focus on nuclear excitation transfer, coherent dynamics, as an explanation for cold fusion. And as Peter has become prone to say, many of those models, actually all those models, are buried in the backyard. But this one isn't. And we think that this one has sort of survived quite a stress test over the past sort of 8 months or so. And hopefully this will get some attention. We think this model, with our calculations, now actually produces observable cold fusion rates, and also goes a long way to explaining excess heat effects. So let's start in '89. There are two sort of canonical papers, a physical review letter by Leggett and Bain, and a letter to Nature by Kunin and Naunberg, which basically calculate upper bounds on the cold nuclear fusion rates in metal hydrides or metal deuterides. And in the case of Leggett and Bain, they sort of start off their article by asking the question, can you accelerate cold fusion rates either by a many-body screening effect or some sort of solid-state effect to enhance nuclear cross-sections, or, quote, an exotic mechanism relying on coherence between fusion processes involving different deuteron pairs. And they say, we focus in this letter on the first possibility, that is, many-body screening effects. And at the end, when they calculate an upper bound, which is too slow to be observable, they conclude by saying, in a macroscopic system, at least this number being a very large number, of atoms would have to collaborate to achieve the required enhancement. While we have not been able to rigorously rule out such an exotic long-range effect, operative only at finite temperature, it seems extraordinarily implausible. But our treatise sort of demonstrates that actually we think we have found such an effect. And Kunin and Naunberg provide sort of very straightforward, we would sort of call them sort of like a spontaneous fusion rate of 3 × 10⁻64 for a pair of deuterons. And so we'll use that for the rest of the talk. So why is any of this possible? How can we accelerate? What would such a long-range quantum process entail? So there was a 1965 physical review letter which called Nuclear Superradiance in Solids. And it builds upon work by Robert Dicke in 1954, also in a physical review letter, which explains the phenomena of superradiance, where if you have, in a two-level system, if you have excited states, if those excited states are coupled together, then instead of decaying independently, they can decay together as a single quantum object, and the decay rate that you obtain is much, much larger. Instead of scaling like n, it can scale as n squared. The other curious phenomena about this process is that also if you have ground states, the ground states, as you have more ground states, will enhance the decay rate of the ensemble. And in this physical review letter, Terhune and Baldwin apply this approach to nuclei, and hence nuclear superradiance. They say the usual assumption that each nucleus radiates independently of the states of other nuclei in the system is incompatible with the coupling of the nuclei through the common electromagnetic and phonon fields. So I'd like to provide a sort of a taxonomy for LENR. You can break it down, at least the way I like to, is sort of into excess heat observables and observables that are correlated with excess heat. Nuclear particle emission, both unconventional nuclear products, but also low-level DD products as well, and transmutations, fission, and also particle capture, which has been reported on very well by Iwamura and colleagues. So let's start with excess heat. This is, I think, what most people here care about. So we can naively start with an idealized picture. And so when we talk about nuclear excitation transfer, when Peter talks about nuclear excitation transfer, you can start by the sort of idealized case where a decay of a D2 excited state to a helium-4 ground state is coupled with a perfectly resonant excitation of a helium-4 to a D2 state. And in such an excitation transfer process, which is essentially a fusion process, you penetrate the Coulomb barrier twice, hence e to the minus 2g. So you have to take into account the gamma factor twice. A quick comment about how fast you need the fusion rates to actually be for your model to work. First, you need it to be observable. That should be obvious. And our estimation is something like 10 to the minus 23 fusions per second would achieve that goal. But in a model such as ours, you also need to be faster than the decoherence time, which I'll make a comment about in just a moment. But that's substantially faster, 10 to the 9 per second. And if you do the calculations for this kind of setup, you have a min and a max. And the min is sort of the minimum without the Dicke superradiance help, without that boost. And then the max is, in the most optimistic scenario, once you do one fusion, the next one's faster and the next one's faster. And so the max would be what's the peak of that Dicke enhancement. And the coupling we use is a relativistic phonon-nuclear interaction, which is a shame that Peter isn't here to explain further. But I will point you to his paper last year in the Journal of Physics B. And just to compare with Kunin's rate, you can see that it's substantially faster, but still it's not observable, and still it doesn't beat the decoherence time, in particular the minimum. And so when we talk about the minimum, you can see here as a function of time, we start. Go here. You can imagine a sort of a group A. These are the donors, and group B. These are the receivers of the nuclear excitation transfer. And you can start with you can assume a group A of 4 pairs of deuterons and 9 receiver states of helium-4. And so after the first one happens, you get this Dicke enhancement. And then after the second one happens, it's faster still, third one still, and so on and so forth, until you reach the peak. But in order to go along this curve and to take advantage of this enhancement, the first rate, the initial fusion has to be fast enough to get started. In all of Peter's models, if you assumed you had already started, you could explain cold fusion. But getting started is the really tricky part. So again, we have the observable rate. That's obvious. But then the decoherence rate. So the decoherence rate comes from the summation of two rates. One is gamma sub M2. And this is the M2 radiative decay of lattice nuclei, which will make more sense why that's the rate that's operative in just a moment. But the M2 radiative decay is associated with the phonon-nuclear interaction as an M2 multipolarity. And then plus 1 over tau D2. This is the dissociation time of a dideuterium in a vacancy of a palladium nucleus, of a palladium lattice. Okay, but we don't have helium-4 in abundance in our system. It's a metal deuteride. But we have lots of palladium. So you can have a hypothesized excited state of palladium, which could be that resonant receiver of the D2 to helium-4 transition energy. And one of the advantages that comes here is that you can have excited states of palladium which I'm noticing now that this says helium-4, but this should be a palladium ground state here. But the advantage that you get here is that you only have to go through the Coulomb barrier once. So only for the D2 to helium-4 transition, whereas the palladium excited state doesn't need to go through the Coulomb barrier to absorb that nuclear excitation. Again, we have our observable rate threshold and our decoherence time threshold. And then we start to get much faster rates. Right? So 10 to the minus 15 at the minimum, and then once you get to the full Dickey enhancement, 0.28 or something in that range per second. But still, 10 to the minus 15 is not good enough. Is not good enough to beat the decoherence time. It is observable, but not good enough to beat the decoherence time. You can't build up the Dickey factors. You cannot get excess heat from this. You might be able to get LENR effects, but not excess heat. But we are making substantial progress and departing quite a bit from Kuhnen and Naunberg's rate. Okay, so we can actually model this. So what I'm about to show you on the left here is the spatial wave function, or the probability. This is the nuclear spatial wave function. These are real wave functions. So this is the probability that if you were to sample this spatial extent, that you would find nucleons from the 4-nucleon D2 excited state system. And on the right, you have the same, but for palladium. And then you can zoom in on the nuclear scale. And once you start introducing vibrations, say acoustic phonon modes, you can start to get Rabi oscillations, or transfers of the probability, of the occupation probability of this nuclear excitation. And so you can see on the left, we're now in sort of the D2 state. That energy then gets transferred, and you get a decay into the palladium, into the helium-4 ground state here. And concomitant with that, in parallel, you get an excitation of the wave function of on the palladium side. But we don't have such a hypothesized, idealized, perfectly resonant 23.85 MeV excitation state in palladium. But we can make use of many transitions, lower energy transitions. One of the advantages of doing so with low energy transitions is that the M2 radiative decay will be much slower. It scales as you get to higher and higher energies. So this helps us out on the decoherence time. And we made use of TIN 120 nuclear excitation data because the M2 excited states for palladium have not been calculated yet, and TIN 120 seems good enough. And so you can see that we can get a pretty good nuclear density of states at the 23.85 transition quanta that we want to transfer to the palladium system. And we can calculate fusion rates. So on the x-axis here, this is the energy dissipated by the acoustic phonon modes from a high-power transient into the system, which facilitates the relativistic phonon coupling. And on the y-axis is what we call an O factor. You can think about this sort of as a correction to the strength of the M2 radiative decay as you get to higher and higher energies. But this defines a parameter space upon which you can beat the decoherence time, right? So this is, the color here is gamma min. This is screened at 350 electron volts of screening. And 10 to the 9 was that threshold we needed to beat. We do that. This whole parameter space is fair game. The problem is if you take a look at the x-axis, the phonon energy that this would require is unphysical, let's just say. So what's the problem? Well, so you can see here, if you make use of these low-lying states, the graph I've shown here on the right plots the gamma transfer. So this is the excitation transfer rate. This is the cold fusion rate you can think of. And on the x-axis, you have the quanta of energy to be transferred in your excitation transfer, right? So this is, in our case, 23.85 MeV because we're transferring the D2 to helium-4 transition. And then the different curves represent different amounts of energy dissipated into the acoustic phonon modes to achieve that coupling. And you can see that at 23.85 MeV, if you intersect with, let's say, 1 joule of dissipated energy, you're not fast enough. We need to get to 10 to the 9. We need to be way up here. Now, if you had a fusion transition, which had 60 MeV to transfer, then you would get into the observable range, and you'd beat the decoherence time. So there's some missing energy that we need. Where can that come from? As Peter as Peter often says as well, this picture is good, but it's actually broken. We need to take into account the fact that nuclear states can exchange phonon energy. So they can both give energy to the phonon field, they can take energy from the phonon field. And this has resulted in adjustment of the generalized nuclear density of states, where again you have density of states on the y-axis, and on the x-axis you have the amount of energy put into the phonon modes, acoustic phonon modes. Okay, now we're getting close. So in the red line here, you have that quantum of D2 to helium-4 energy, 23.85 MeV. And it intersects with this curve, which is the same curve as I just showed you in the previous slide for 1 millijoule. So that's manageable. We can do that. And you can see that, it intersects, but it's not fast enough, right? It's not fast enough. You need to get to 10 to the 9. And then you can sort of say, well, actually, with the exchange of phonon modes with palladium nuclei, the quanta of energy that could be taken up by a palladium nucleus is not necessarily 23.85 MeV. It can be less, and it can also be more. And there's a probability distribution that it'll be less, and a probability distribution that defines on the greater side as well. Most likely it'll be 23.5 MeV, but there's a finite probability that it could be much, much higher energy. Say, for example, you added 20 MeV of phonon energy into the excitation transfer process. Then you intersect with that millijoule phonon curve here, and you've boosted by 6 orders of magnitude. So So then what you have to do is you basically have to take what is the average amount of energy to be transferred to the palladium nucleus, and what would the rates that would entail be? So you take basically like a weighted average. And when you do that, you get this curve. It doesn't look very exciting, sort of simple, but I'll show you quite a bit of work went into this. And what you see is on the x-axis, you have the amount of energy dissipated into the phonon modes, and on the y-axis, you have the excitation transfer rate, i.e. the cold fusion rate. We should just remind ourselves how much progress has been made in the last 8 months, really last 35 years that Peter's been working on this. We started with 10 to the minus 64. We need to get to 10 to the 9 to beat the decoherence time, or be competitive with it, to start to build up the Dickey factors. That would entail something along the lines of a millijoule of energy dissipated, or 1 watt of power into a high power transient phonon mode at 5 megahertz. That seems doable, and we can get to 10 to the 9. We can be observable. We can beat the decoherence time. Now, this community will care about excess heat, right? So this is, if you remember from last year in Poland, Peter shared his calculations on nuclear molecule states. So these are these excited states of palladium, and compared with the D2 to helium-4 states. And you can see that if you can get to this high energy range, right? So if you can get to this high energy range with the 23.85 MeV plus the phonon energy that has a finite probability of being added in the excitation transfer process, you can get to a really high density of states. So high, in fact, that you can start to decay from nuclear state to nuclear state to nuclear state by optical phonon or plasmon emission, i.e. heat. So this is sort of the, if you take away one thing from this presentation, it would be this graph. Again, on the x-axis, we have the amount of energy dissipated into the acoustic phonon modes. And on the y-axis, we have the number of helium-4 nuclei. So this is sort of the nuclear ash, right, for the D2 to helium-4 fusion transition. And you can think about this as the tally of fusion reactions which have occurred throughout this process. And if you remember, this is one of these sort of unintuitive parts of Dickey enhancement, is that the higher number of ground states which you have in your ensemble, the faster you go. And what this really sort of starts to entail, and you can just sort of take a look at the absolute numbers of the rates we're talking about here, extremely high. If you get into a particular regime in the upper right part of this figure, you start to enter a runaway reaction. What this would look like is melting of a sample. Or there have been some of the senior members of the community will remember reports of runaway reactions in excess heat experiments. This would explain that. So that's sort of like the central message of the talk. I'll then quickly sort of say a quick bit about nuclear particle emission. So you can imagine as nuclear particle emission or transmutation being the result of when things aren't working well. If you transfer 23.85 MeV quanta of energy from the D2 to helium-4 transition, if you transfer that to a palladium nucleus, but you can't get higher, Maybe you don't have phonon energy to transfer. Maybe the coherence sort of breaks. Then you're left with an excited palladium nucleus with 23.85 MeV excitation, which will disintegrate. And it'll disintegrate something like this. So you have a palladium deuteride. You're stimulating it with these phonon modes. Now we see that same picture that we saw a few slides earlier with the D2 and palladium nucleus. The D2 being presented here, which then can decay into a helium-4 nucleus, which is very concentrated right on the nuclear scale versus the atomic scale. And concomitant with that, you'll see, so right now we're in the D2 excited state, transfers to a palladium state, and you'll see in parallel excitation of the palladium nucleus when this is blue, i.e. when this has been decayed to helium-4. But you can ask the question, this is sort of excitation transfer back and forth. What happens if you're playing this game of musical chairs, and it stops? Maybe you lose that relativistic phonon nuclear coupling. I don't know if you missed that, but you can basically get a disintegration of the lattice nuclei by emission of protons or neutrons or alpha particles, depending on the energy and the ionization energy for that particular isotope for neutrons, alphas, protons, etc. What about transmutations? I'll focus here on fission. You can imagine two scenarios. One, like is shown here. You have, say, 2 D2 to helium-4 quantas transferred to a palladium nucleus. Now you've gotten up to a much higher density of states. Maybe still not high enough, right, to start to decay from state to state to state by phonon emission or plasma emission. So not enough to get to excess heat, but things break. But they break with enough LENR activity such that you can get, again, lattice disintegration, or a disintegration of the lattice nuclei. In the prior case, we were at a low enough energy where that disintegration might happen quite asymmetrically by nuclear particle emission. But when you get to higher energies, maybe by, say, 2D2 to helium-4 transitions, 2 fusion decays, or by some amount of phonon energy, maybe, again, not enough to get to excess heat mode, then you can get a disintegration of the nucleus, but a far more symmetric disintegration of the nucleus, a fission reaction. And this is sort of shown very beautifully. We still don't have isotopic data on this, but this is sort of what we expect this to look like. A sort of morphological feature like Babarian showed here in his paper from last year and presentation from several years ago, where concomitant with the morphological feature, you see a reduction in the palladium peak from the EDX spectra and many low Z, new low Z elements produced. Whereas outside the morphological feature, you see the large palladium peak and none of these other low Z elements. And this is, of course, replication from Ubaldo Mastro-Mateo's study in 2016-2011. I had the great pleasure to go visit Ubaldo at his lab. But the key sort of message of why this sort of is indicative of transmutations is that if you then go look at those elements that Jean-Paul identified, they turn out to be pretty good matches with the expected fission daughter pairs of palladium nuclei. So with that, I'll go ahead and take some questions. But just before I do, I just want to thank all our colleagues and collaborators and supporters and funders. I've listed many here, but I'm sure I've forgotten some, and to those I'm also very thankful. And then, of course, to the support that makes this all possible from ARPA-E, from the Anthropocene Institute, and then for myself from the Winton Program for the Physics of Sustainability. Happy to take any questions.
Okay. Thank you, Jonah Messinger. Conrad.
Okay, I have 3 different... Please wait a little bit, yeah? So I have 3 different points. First one, if you compare your results to the screening, you shouldn't do it with the Kuhn data because he made a large mistake. He calculated screening energies for hydrogen molecule. But if you are working in the metals, the screening energy is at least a factor of 10 larger. So then you have increase of the reaction rates at room temperature 40 orders of magnitude. So you should, if you want to compare, something with the screening, you should take into account this screening we measure usually for over 30 years. This first point. The second point is that if you are speaking about Dickey enhancement factor, there is, of course, can be very large, but it is a very rare event. If you study on average a little bit longer time, you have a usual Poisson distribution. You have nothing, no enhancement. Of course, you can speak about some coherent states, but you should take into account thermal movement for that. And there is very quickly you have decoherent situation. The second point. And the third point, if you compare to the resonance states levels in palladium, there are not simple levels, they have widths. They are overlapping, and then there is the mechanism, you cannot distinguish between individual states. So there's not a correct picture you are speaking about. Okay, and yeah, we can discuss later something more.
Sure.
So I'll try 3 points. Okay?
I'll try to take those in turn, but you might need to remind me. So on the first point, we assume in our SI 350 electron volts of screening energy. You still need to make up to go from Kunin and Naunberg's rate of 10 to the minus 64 to 10 to the 9 to beat the decoherence time. You're still talking about 75 orders of magnitude. I find it unlikely that electron screening alone could make up.
No, this really a large mistake. To that time, there was why the Department of Energy to that time, there was 93, rejected the proposal to study cold fusion in the United States. Because of this paper of Kunin. Yeah, Kunin was one of the famous nuclear physicists. And he made a large mistake, putting this kind of estimations to that time. Okay?
That's fine, but I just went through explaining how we can beat Kunin's rate by tens of orders of magnitude. My point is simply that to make up the 75 orders of magnitude, it still seems unlikely that one can do that by electron screening alone. On the superradiance point, so normally superradiance, right, is widely used at the optoelectronic energy scales, but it's no longer just sort of a theoretical point. I forgot to mention this on this slide. It's no longer a theoretical point. This physical review letter in 2018, I'm sure you're familiar. Yeah, you're familiar with this. Chumakov et al. In Nature Physics reported on the 15-fold acceleration of the decay of a coherently excited ensemble of iron-57 nuclei by an X-ray-free electron laser. 15-fold acceleration going from an ensemble of 2 to 20 nuclei for the initial decay of the ensemble. So 10-fold increase in the ensemble, 15-fold increase in the acceleration. That's evidence of nuclear superradiance. So we do have evidence now of physical evidence of nuclear superradiance. And so
Okay, but I can give you some, but maybe we discuss later.
Sure.
Okay, Dan, and then Dimitar after that.
With regard to the interchange of energy from the phonon kinetic energy to the kind of electromagnetic energy that you would need to affect transmutations, I'm not hearing how much energy exchange or what type of energy exchange you're expecting there. The second law of thermodynamics says that there is going to be entropy production, and you're going to have losses. You seem to be talking about something where the energy is transferred 100%, and in these systems, it's anything but that. Okay, the percentage of loss is quite high. But also the first law of thermodynamics, you're talking about the generation of a lot of phonon energy, a lot of kinetic energy, okay, as they do in the tokamak. But I'm not hearing how you're accounting for the localization of that energy in a way that it can cause a transmutation.
It's not. Okay, I see what you're saying. So it's the dynamics are not occurring with localized energy. It's basically like you have a superposition state, delocalized state, and then you make an observation. When you make the observation, that's when the transmutation would occur, if that makes sense.
But the energy has to be localized.
Yeah,
You're
but
not going to get a transformation occurring because you have a lot of kinetic energy all over the place.
it's not. I mean, well, so there's the relativistic phonon nuclear coupling, which is the method by which the delocalized state is coupled together. But it is a long range effect. It's not a localized effect.
Okay, Demeter?
Okay. It will correlate to the previous question today to you. In any case, there is repulsion between nucleus. I didn't see any correlation in your actual theory related to the elimination of this actually repulsion between the interacting nuclei. Let's see, two deuterons. Okay, what is the correlation? You mentioned here about phonon energy. The phonon energy, if you consider actually the maximum phonon energy, is not enough. In order to make something like to compensate the repulsion between two, let's say, deuterons. Otherwise, actually, the theory is very beautiful. But how does it correlate with the repulsion between the nucleus? They are positive charges, doesn't matter. Hydrogen or deuterium. How does it correlate?
Yeah. Okay. I don't have a great slide for this. So we're not ignoring Coulomb repulsion. The Coulomb repulsion is the reason why Coulom's rate is so low. So we're taking, we account for Coulomb repulsion. In fact, actually, I know what I'll show here. Right. So you can see here we take into account Coulomb repulsion in the e to the minus g. We take into account the gamma factor. What we're saying is that the Dickey superradiance effects can overcome, can substantially far and away overcome the Coulomb repulsion.
But how? What is the mechanism? How it will be overcome?
Right. So if you have many excited states, if they're decaying together, then they don't just decay to one state. It's one single quantum object. So they can essentially the best way of imagining this is that they can decay to any of the ground states in the ensemble.
And we're going to reach these actually higher states.
What did you say?
Okay, these actually higher states, how can be reached by, let's say, some kind of incorporation of additional energy in the system? Is it possible that these higher energy states to be reached in solids? In order actually the Coulomb interaction to be overcome?
Are you talking about on the palladium side?
Doesn't matter where.
I don't understand the question.
No, doesn't matter where. Even if it is on the palladium side.
Exchange of energy between the palladium excited states and the phonon energy.
How?
The relativistic phonon nuclear coupling. You can read the paper.
Yeah, may I suggest we discuss this outside?
A question from Jean-Luc Payet.
Jean-Luc has a question. Did you want to do one more question?
Oui.
Do we have one more question?
Yeah, Jean-Luc, you can speak.
Oh, yeah. Go ahead,
Monsieur,
Jean-Luc.
your presentation is very, very interesting, but I didn't see where quantum physics comes in.
That is a wonderful intro to my colleague Matt Lilly for his presentation.
Okay.
So I think that will be made more clear in Matt's presentation.
Thank you, Jonah Messinger. Thank you so much. All right.